Hi, welcome back. In this lecture, we want to start talking about the dynamic deployment model. Many people know this model as the system status management approach. System status management is defined by Jack Stout as the art and science of matching the production capacity of an emergency medical service system to the changing patterns of demand placed upon the EMS system. Another definition that's included in one of the references you have as a reading is making the most system status management is making the most efficient use of whatever resources are available at any given time and planning effectively so that the resources available will be adequate to meet the demand made on the system. When you think about deployment planning, good deployment planning takes several things into consideration. It takes into consideration how you can evenly distribute workloads, which is actually part of the lean way of thinking about organizational improvement. It minimizes response times. It includes time to maintain vehicles because that's an important component of fleet maintenance function. It provides geographical coverage because that's an important component of providing EMS. It decreases employee stress by mixing emergency and non-emergency requests where appropriate and where the capacity exists to do that. It reduces mandatory overtime, which we'll see in week 2. Many people don't think about that as being an issue related to deployment, but it definitely is. And it's employee-centric in terms of scheduling. Well, we need to look at a little terminology that we'll utilize both this week and next. First, again, is the unit hour. A unit hour, again, is simply an ambulance staffed and ready to respond for 1 hour. Unit hour utilization is, specifically when we're talking about transport unit hour utilization, is the ratio of staffed unit hours to transports. Now, some folks have advocated that we should utilize dispatch unit hour utilization, which is the number of calls that an EMS crew is dispatched to. But again, the reason it started out as transport unit hour utilization was simply because that's what's tied to the revenue stream in terms of how we're reimbursed currently. Some people do look at some other factors such as total busyness or total, what's the other word that some people use, total workload, total workload. So those other types of looking at it are important, but we have to keep in mind the fact that this is the current revenue stream, and that's one of the reasons to look at it from this perspective. You'll also hear people talk about requested unit hours and effective unit hour utilization. Requested unit hours and effective we'll talk about more next week. That has to do with the number of unit hours you feel like you need for a given day of the week, time of day, and the effective is how many you're actually able to staff. And it's important to look at that because if you're simply looking at the schedule and comparing it to your response time capabilities or performance during maybe the previous week, you may look at it and think that you need to add more unit hours when in fact all you need to do is actually put the number of unit hours that you had originally forecast actually on the street to provide service. So we'll talk about unit hour demand, which is the hourly analysis of call volume, and that's for all 168 hours of the week. Now, the more hours you break it the week into, the more iterations you have, the more complex your system status planning model becomes. Also, the more complicated, if we use something like computer simulation that we'll talk about next week, the more complicated the statistical models and the statistical analysis becomes. So where possible, we want to identify similar hours or days of the week. And in most systems that I work with, you come nowhere near to seeing 168. It's usually more something along the lines of a number of 6 different system status plans that you need to create as opposed to a system status plan for all 168 hours. But we'll talk more about that specifically next week. Peak load staffing is definitely another piece because what we're trying to do in terms of a dynamic model is match supply to demand as much as possible. So scheduling the number of units needed to meet the hourly demand is crucial because without being able to do that, we're unable to put the ambulances in the location, the response vehicles in the location they need to be to respond in a timely manner to maintain that response time requirement that we may have or that we're imposing upon ourselves. Variable staffing is also important. That's the use of several different shift lengths to meet the hourly demand. As I mentioned in the previous lecture, that's one of the things that can greatly impact the cost of a deployment model. We would like as many variations as possible in terms of shift length. I've actually worked with some private companies that actually have shift lengths of 2 to 3 hours that they'll have a crew come in when they know it's going to be a very busy time. Unfortunately, I don't think that's the optimal. I think that's very hard on employees. But definitely you should be thinking of evaluating the system to that level of granularity to understand how that would function such that you can provide the best service possible with the resources you have. Unit deployment, that's the geographical distribution of units designed to best position the available resources to respond to the next received request for service. And that's one of the reasons we'll talk about from the dynamic perspective of moving the ambulances to the appropriate location based on how many ambulances that are left in the system. Simple average demand is the average number of calls received per hour. The high average demand is demand divided into 4 groups, and then the highest is taken out of these 4 groups. And I should add the calculations that you see here are based on the original system status planning analysis or demand analysis. And we'll actually see in the next lecture how you can create these in Excel. But the reason they were created, simplistic as you see here, such as the high average demand, the reason it's divided into 4 groups and then the highest value of each of the groups are averaged is because historically when system status management got started, it was far enough back that computer power was very limited and most places did not have computer capability. So the idea is to create a very simplistic back of the envelope or napkin model, if you will, way of analyzing this to determine how many ambulances you should put in place. But next week we'll see that through operation research there's definitely a ton of models and research has been done to actually evaluate much more comprehensive and exact modes than doing that, than analyzing demand than these. However, these are the models that were in the original historical way of doing it. The peak average demand there is as above, except you divide it into 10 groups instead of 4, and then you create the average from those 10 groups. And then the high average demand is the highest number of calls in that period of time. Historically, 20 weeks of data were utilized, and in most places I still see people historically creating 20 weeks of data to do demand analysis, and you'll see why that's important in a slide or so, because you would have to repeat it to go through the iterations of this process. But there's nothing magical about the 20 weeks. The number of weeks that are necessary in terms of the sampling should be based on sampling theory and are largely based on the number of requests you have in any given hour during any given week. So your demand should determine the number of weeks that you need to actually let the system operate, if you will, before you actually do the next demand analysis to see if there's been a change. So here are the steps to creating a dynamic deployment model or a system status plan. Again, we start just like in the static model by doing the demand analysis. And we'll talk specifically in the next lecture about how to do it the historical way, and then we'll talk next week about how to do it in a much more complex way. Next, you determine the number of resources needed for each hour of the week, all 168 hours. Now, quite often that's not done in a static model because we're not interested in understanding demand for all 168 hours because we're not willing to use varied shifts or peak load staffing to actually match supply and demand. It's interesting that a lot of statically deployed resources, a lot of fire services that use static deployment are beginning to experiment with using dynamic deployment simply because they realize they can't afford to put the resources in the stations to basically be idle during non-busy times. And that's especially, again, true because they're seeing their mission transition from one of fires to being one of life safety. The next step is to conduct a geographical analysis of call distribution, and that's actually to look at where the calls are taking place. Again, we talked in the last lecture about a couple ways you can do that in terms of mapping. You could use something like Google Maps, you could utilize a map point, or you can utilize a much more sophisticated something like ArcView to actually better pinpoint that. If none of those exist, you can simply use push pins on a physical paper map that you place on the wall, taped to the wall, and actually use push pins. I've actually done system status plans utilizing push pins to evaluate where the calls are at, and it works very well. Next, we develop the system status plan. We implement the plan, we refine the plan, then we refine the plan, and we refine the plan. A good system status plan will take, based on experience of people that have done a lot of plans, about 2.5 years to tweak to get the system in line. And then, of course, it's going to change periodically simply because you have a change in demand or call volume. Now, when we think about demand analysis, we're going to talk about looking at hourly demand analysis, but definitely there's other things you want to look at as well. You want to look at yearly demand, and there something like regression analysis is appropriate, where we can look for the variables that contribute to overall yearly demand. Now that helps some, but that doesn't help us a lot in planning overall resources because that one large number doesn't tell us much about matching supply and demand at the street level. So that brings us to the next step, which is to look at daily, weekly, or monthly demand. And there we can even use something like time series analysis. And it is important to look at that because one of the things we want to do is, in addition to creating a system status plan based on a demand analysis for the last, say, 20 weeks, to use the historical figure, in addition to doing that, we need to think about what the growth is potentially going to be like over the next period of time. And that's especially important if you work for a municipal agency where budgeting is such an issue and you're going to have to budget well ahead of time to be able to add a resource. You need to be able to plan that. And then finally, there's hourly demand. And hourly demand is really what comes into play when we're actually getting down to determine how many ambulances we have at any given time of day and where they'll be geographically located. Now, with daily, weekly, and monthly demand, again, we can look at things like seasonality, we can look at trends, we can look at major fluctuations. All of those things are important to look at and are something that should be looked at in conjunction. But often, usually, they don't affect or drive the normal system status plan. One of the reasons we routinely conduct the hourly for all 168 hours of the week demand, as you'll see in a few minutes an example of that, the reason we do that is because that allows us best to plan our daily approach to covering the geography. Now, there are other time series methods, and all of these can play a role, and all of them are important, but they're marginal in comparison to um, looking at hourly demand. Now, the one place these will play a role, again, is if you're in a municipal organization and you're looking at planning over the long term, and you know you need to plan ahead of time for how many ambulances you may need. It's not going to help with what time of the day you need those ambulances or where they need to be, but it'll help you theoretically to plan how many you need to budget for in the future. So with hourly demand, we said we could take something like the last 20 weeks, and I'll use that number because, again, that's what's been used by Stout. And there's no statistical validity to that. It's just a number that he chose. And the issues to consider are, the things we talked about before: the seasonal variation, the population growth, and the hourly variation. The hourly variation is really the key component. So then the next thing we want to do is actually calculate these summary statistics. And often they'll look something like this. Here you see an example of a Sunday. And in this, if you'll look, I'm going to try to use my cursor here so you can see. We actually have the dates. We have the hours across the top. We have the total number of responses during that 24-hour period. Many of your numbers will probably be much smaller than this. If we look down at the bottom, ignore this piece. We'll come back to it next week. But we have the traditional EMS demand analysis statistics. We have the maximum, which is the maximum number that happened or that in that period of time. We have the standard deviation, which is the mathematical arithmetic standard deviation. We have the average, which is the arithmetic mean. We have the average high that you saw earlier, the average peak. We have the 90th percentile. We have the smoothed average peak. And then we have one other one at the bottom, and we'll talk about it again next week. But what we're actually going to talk about next week is this component in the middle, and how it gives you a whole lot more statistical power in your predictions than these historical methods that you see at the bottom. But I do want you to understand these historical methods and have an opportunity to actually try and utilize these. So we're going to go through the calculations of these. Now there's two ways, to do this summarization of the hourly data. As I mentioned, the Stout methodology, which will be outlined in a couple of the papers that you'll have for this week. And then something called queuing theory or waiting line theory, which is what we'll look at next week, which requires more complicated, complex formulas to actually evaluate it. But the benefit of queuing theory is that it includes the unit task time. And we'll see next week why that's so important. Now from this analysis, we determine the number of units that are needed for each hour of the week. And we end up with a summary chart. Here's the summary chart that you saw at the bottom, just a little larger so that you can see it. Now, again, this average task time is actually usually not included. We usually make the assumption that it's 1 hour, and you see here that it's actually less than 1 hour. So we'll talk about why that's important.